Hi, my name's Cassandra, and today we're going to be talking about the research method correlation. In today's lesson, we will be talking about the definition of correlation, the history of correlation, some key characteristics, the different types, when you should use correlations, the steps in conducting correlation, ethical issues and limitations, evaluating correlation, and some examples.
Correlations observe and measure two variables to determine the relationship between them. This is most often used in a group of subjects narrowing in on two traits. For example, a scientist can study the number of hours practiced playing the guitar on performance. This example would be a positive correlation, which means that as the number of hours of practice go up, the performance would go up as well. The opposite, or negative correlation, such as alcoholic drinks on reflex speed, means that as the number of alcoholic beverages go up, the reflex speed goes down. The problem with the correlation is that it is hard to tell if two traits are directly related or not. For example, if scientists were measuring the number of TVs in houses on the IQ level of children, and they found that this was a positive correlation, they have a problem, because these aren't directly related. A large number of TVs in a house could be the consequence of a higher income, which also means that the children in the house probably have more money to spend on education, which makes IQ the result of average income, not TVs.
So, the definition of correlation is the relationship or connection between two or more variables at a time. History of correlation, the themes of origin and development of the statistic tests and procedures. In the late 19th century, the procedures for correlation were developed by Karl Pearson, and the formula for correlation was developed in the late 1800s. Factor analysis, reliable estimates, and regression. Researchers can test variables using correlation statistical procedures through sampling and other quantitative sources. And Ewell, Pearson's student, identifies how to measure more than two variables at once. The uses of correlation are to study two or more quantitative variables, to describe and measure the relationship between two or more variables at a time, and to predict the outcomes. Some key characteristics of correlation are both designs of correlation are key characteristics of their research. There are scores correlated for surveyors reported by researchers. Research is recorded through scatter plots, other designs of data, and correlated materials. Positive and negative relationships, association between scores to see the normal and non-normal distributions and patterns. And if two or more variables correspond with each other, the relationship is changed, and the researcher is only interested in the third variable. You should use correlation research design when relating two or more variables at a time to predict an outcome, when you can apply information and incorporate and calculate the statistical tests. So here you see three different types of correlation design. So we have the positive and negative, which shows when the variables are increasing and decreasing. The simple correlation, partial, multiple, linear, nonlinear. So the positive correlation is the relationship of two variables increasing or decreasing together, and the negative is two variables, one going up and one going down. Number of variables in correlation. So simple correlation is two variables that can rely on each other. Partial is two variables taking away the effects, and multiple are various of different variables which have different values and predictions. So linear correlation is a straight line relationship that follows up the graph, and it shows the correlation between two variables, usually shown in a scatter plot between -1 and 1. So what is correlation?
The correlation coefficient is this really popular way of summarizing a scatter plot into one single number between -1 and 1. And in this video I'll show you 3 formula-free steps to how that's done. Okay, so I'll work with example scatter plots like this. It shows 4 movies. On the x-axis we can see the movie's length, and on the y-axis the rating for the movie between 0 and 5 stars. The first step for the correlation coefficient is that it fits a straight line to the data. So in this example the line would go somewhere like here. And this is your standard straight line fit. So the one that minimizes the square distances between the fitted line and the individual data points. In the second step, the correlation coefficient simply remembers if the slope from the straight line fit is pointing upwards or if it's pointing downwards. So in the first data set, we saw that the slope is positive, and in that case the correlation coefficient is positive as well. I already mentioned that the correlation coefficient is always between -1 and 1, so if the slope is positive, the correlation coefficient will be between 0 and 1. Then in the second case, in this data set, you can see that the longer movies tend to get the worse ratings, so the slope is negative. And in that case, the correlation coefficient is negative as well. It'll be between 0 and -1. And then there's a third case, and that's that the slope is perfectly straight. In this data set, you can see that there's no real difference between the longer and the shorter movies in terms of rating. And actually, if I draw in the regression line, you can see that it's perfectly straight. And in that case, the correlation coefficient is 0. So just by looking at the sign of the correlation, you already know something about your data. If the correlation is positive, you know that the overall trend is upwards. If the correlation is negative, you know that the overall trend is downwards. And if the correlation is 0, you know that the overall trend is level. So now comes the third step, but this one is trickier. So far, we already know whether the correlation coefficient is between 0 and 1 or 0 and -1. But we don't know its magnitude yet. So how big is the value? Is it close to the extreme value, so it's something like 0.92 or -0.92? Or is it small in magnitude because the correlation is weak, so it's closer to 0? The correlation coefficient figures this out by looking at the quality of the fit of the straight line for the data. And I'll try to give you an intuition for this first. So here are 3 scatter plots, and I've already drawn in regression lines. Now, which of these 3 lines fits its data the best? What do you think? Well, so it's this one, because the data fits most snugly around it. And which line fits its data the worst? Okay, so that's that one, because the data scatters the most around it. So in these 3 plots, the highest correlation would be in this plot, and the lowest correlation would be in this plot. Actually, the correlation coefficient for the first plot is around 0.81, and the correlation coefficient for the worst plot is 0.32, so it's much lower. But how does the correlation coefficient figure this out? Well, it compares 2 things. The first thing it looks at is the scatter along the y-axis. So if I draw in the y values, you can see how they scatter along the y-axis. The second thing it looks at is the scatter of the data around the fitted line. So that corresponds to these distances here. And the rule goes like this. The more there's of this in comparison to this, the stronger the correlation coefficient is. Okay, let me show you a few examples. So in this data set, we can see that there's quite a lot of scatter along the y-axis. But there's really little scatter around the fitted line, right? Because the distances here of the data points from this fitted line, they are really short. Okay, so in comparison, there's a lot more scatter along the y-axis than there's scatter around the fitted line. And in this case, the correlation coefficient is really large in magnitude. This is a positive slope, so the correlation coefficient is close to 1. It's actually 0.95, so that's a really strong correlation. And here's a second case. So you can see that again, we have quite some scatter along the y-axis, but in this example, the scatter around the fitted line is also really large, right? The points are really far away from the fitted line. Okay, so in comparison, there's only somewhat more scatter along the y-axis than there's scatter along the fitted line. So in this case, the correlation coefficient is weaker. It's 0.56 actually. That's still decent correlation, but it's less than before. In this third case, the fitted line actually turns out to be straight. So what this means for the data is that the scatter along the y-axis and the scatter around the fitted line, they are actually exactly equal. And in this case, the correlation coefficient is exactly 0. So you can see that if the scatter along the y-axis is much larger than the scatter around the fitted line, then we get correlation coefficients which are really large in magnitude. But if the scatter along the y-axis and the scatter around the fitted line are really similar, then we get correlation coefficients which are close to 0. So now we know the 3 steps of the correlation coefficient. Let's see how this can help us with an example. So here are 2 scatter plots, and the question is, which one has the larger correlation coefficient?
Measuring the strengths of the relationship between two variables, which can range from 1 to 0 and closer the rate is to 1, the stronger the relationship is bivariate correlation. So as you can see, most of these are going up here, and that means that the correlation is very strong throughout the bottom half. And in the top here, the correlation is not as strong. Partial correlation is the degree in which we measure between two variables while controlling variables are removed. So, if you are going to measure the correlation between the red and the blue circles, you would use the 2 colors that correspond in the middle, this part right here and this one right here. And if you were to get the correlation between the red and the yellow circle, you'd be looking at this color here and this one right here. Prediction correlation research design is positively correlated variables that will predict an outcome, establishing a trend based on previous information and establishing possible outcomes to the degree of certainty. An example of this would be if a doctor is predicting that the medication given for a child with epilepsy will help and improve their span of seizures. This could be done through graphing designs and establishing the medium. Explanatory correlation design is the explanation of the degree of association among the independent or dependent variable, and it answers why and shows the cause and effects of the theories. An example of this would be that doctors research what % of pills affect the human brain with epilepsy versus explanatory research, which would tell us how the pills are improving the seizure episodes. This can be done through surveys, questionnaires, interviews, and group discussions. Steps when conducting a study: making a prediction, choosing individual to do the study on, apply 2 or more variables to measure, collecting data, analyze data, and to grasp the concept and reflect on the outcomes. The ethics of correlation: researchers need to find an analysis which must include the size and effect, the correlation statistics, no made-up data, statements on the relationship of 2 variables, and shared data and then published for all to see. Some issues with ethical correlation would be the data is collected through 3 different ways, so through sample size, lack of control, and inclusion of many predictors. Some limitations that can arise through correlation: you cannot prove how the one variable influences the other. Correlation does not determine the direct results, just the relationship between them. And when studying correlation, you can't determine how A changes variable B. Some pros would be that you are able to determine the relationship between both variables, and the con would be that you can't determine how the 2 variables will change each other. Evaluating correlation, you can do this through sample size, graph presentations, procedures, and relationships of the variables measured. When evaluating the study of correlation, you must observe the data collected, analyze, and interpret.
Once you've described behavior with surveys, case studies, or naturalistic observation, you can start making sense out of it and even predict future behavior. One way to do that is to look at how one trait or behavior is related to another, or how they correlate. So let's get back to my buddy Bob, who seems to think that his refrigerator is actually some kind of time machine that can preserve food indefinitely. Let's say that Bob has just tucked into a lunch of questionable leftovers, pizza that may very well have had a little bit of fungus on it, but he was hungry and lazy, and so he doused it in sriracha. Suddenly, he starts seeing things. Green armadillos with laser beam eyes. From here, we could deduce that eating unknown fungus predicts hallucination. That's a correlation. But correlation is not causation. Yes, it makes sense that eating questionable fungus would cause hallucinations, but it's possible that Bob was already on the verge of a psychotic episode, and those fuzzy leftovers were actually benign. Or there could be an entirely different factor involved, like maybe he hadn't slept in 72 hours or had an intense migraine coming on, and one of those factors caused his hallucinations. It's tempting to draw conclusions from correlations, but it's super important to remember that correlations predict the possibility of cause and effect relationships. They cannot prove them. So we've talked about how to describe behavior without manipulating it and how to make connections and predictions from those findings, but that can only take you so far. To really get to the bottom of cause and effect behaviors, you're gonna have to start
So this video is about how correlation complements other research methods and the limitations of correlation. So when studying correlation, you have to remember that it predicts the possibility of cause and effect, and it cannot prove one. This is another example of correlation. So you can see here, there's the negative correlation. So the slope is going down, and you can see that the variables are a little bit spread out, not as dense. And on this side, you can see the positive correlation. So all the variables and data collected are very close and following the positive increase line. And then here you can see that there is no correlation because all the data is scattered. This is another example of correlation, an orange and a lemon, because they're both in a fruit group, but they have no relation to each other. So in summary of my presentation, in order to find correlation, you must find the relationship between two or more variables. There are many different ways that you can do this, such as through surveys, data collected, interviews, etc. There are many different ways and types of correlation, such as positive, negative, simple, partial, multiple, linear, and many more. And the most important thing to remember is correlation does not equal causation. And these are my references. And here are some questions that you could answer for me. So in your own words, describe the meaning of correlation. In what situations would you use correlation research design? How was correlation designed and what influenced the development? What are the negative and positive effects of correlation? And in what ways can we measure correlation? And do you have any questions for me?